Welcome to podcast number 142, and in this podcast we're going to be talking about the second half of the podcast series. So in the last podcast 141, we covered some of how different wheelhouses affect the drag of a car. We looked at three different types of wheelhouses, one from Audi, one from Toyota, and one from Mercedes. They differed in how blocky they are, and with the Audi being the most completely semicircular, so you can see here in this figure that it's almost like you get a circle and you cut it in half. Then the Toyota, which was a RAV4, was sort of like a hexagon but cut in half. Then the Mercedes was a lot more like a rectangle cut in half. So the Audi produced the lowest drag coefficient of 0.4225 for the armored body it was put on, while the Toyota had a drag coefficient of 0.434 and the Mercedes had a drag coefficient of 0.442. Now, I mentioned in the last podcast that the CFD setup for this paper wasn't that good, so there were some questions that arose. So the actual values that we just quoted there, we're going to ignore because these values are probably only a few percent different, and possible problems with the CFD would easily eclipse these percentages, so I don't really think we can trust these values too much. We're really going to be focusing more on the flow physics in this podcast because I think we can trust that a lot more, because to get the flow physics to be right, you don't need to have nearly as an accurate CFD as if you want to get the force coefficients right, because there might be some small differences in the flow physics, but it's not really that discernible to the naked eye, so we can really trust the flow physics better. And to look into this topic, we're going to be looking at a paper again called Investigation of Wheelhouse Shapes on the Aerodynamic Characteristics of a Generic Car. And again, this is open access, so you can find a link in the description. So let's continue where we left off from in the last podcast. In the last podcast, we just went through this figure here. And if you're just listening to this on Spotify, you can watch the video on YouTube and or Spotify. So this figure here, figure 9 and figure 10, we went through in the last podcast. Now let's move on to figure 11, where we can see the turbulent kinetic energy plots in the wakes downstream of the cars with the three different wheelhouses. So the Audi, which is the top, the RAV4, which is on the second line, and the Mercedes, which is the third line. Now, I'm a little surprised at just how different these wakes are between these different wheelhouses. The Audi and Mercedes wheelhouses produce somewhat similar turbulent kinetic energies in that the maximum is seen around 1.4. So you can see here 1.4, 1.4. But the Toyota wheelhouse produces significantly less turbulent kinetic energy, which indicates less jumbled up flow. So you can see here in case 2 that the turbulent kinetic energy doesn't really get very close to 1.2 at all. It stays more like in the 0.4 range. Now, the turbulent kinetic energy isn't everything, but it is a decent indication of how much energy is caught up in the flow features that aren't inherently good for aerodynamics. So if you have more turbulent kinetic energy, often that indicates that there is like some sort of vorticity or whatever happening, and we usually don't use those vortices for anything good, unfortunately. So that's really just wasted energy, and that means that it's more drag. So that's a general indication of the TKE. But let's move on to some other properties such as streamlines. So the researchers also process the data to give streamlines, and if you don't know what streamlines are and how they differ to streak lines and path lines, check out a video on YouTube called Aero Fundamentals number 9, where we explain the differences between these, and quite well, if I do say so myself, because I think generally speaking, the difference between streamlines, streak lines, and path lines are not really harped on about a lot, so we often get confused between them, but there is quite a big difference, and we go to that in number 9 in the Aero Fundamentals. So in figure 12, they show some instantaneous streamlines behind the car, and one thing that I should mention before describing them is that the instantaneous streamlines are good, but they don't tell the whole story, and that is because they change with time. They're instantaneous. So you might get some screenshots of streamlines at one point in time. That doesn't necessarily tell you the whole story, because it might look like one kind of figure in one point in time, but then when you jump to the next point in time, the streamlines have changed dramatically, and it turns out that maybe you just happened to see a good instant in time, so you got this somewhat warped picture, and you thought maybe, okay, the flow is much more streamlined than what it actually is. So a time average streamline is more helpful usually, but instantaneous streamlines also have their place. One major benefit of instantaneous streamlines is that they can show transient flow features, which is something that time average streamlines can't do, because time average streamlines average everything out. So a flow feature that might only be present for a few tenths of a second each second might get averaged out by these time average streamlines, but for instantaneous streamlines, you can see them. Anyway, let's discuss what we can see in figure 12, and we need to take what we can see with a grain of salt, because they are instantaneous. So from figure 12, the wakes of the armored body with the Mercedes wheelhouses looks very different to the other two. So this bottom one here, figure 12C. The other two wheelhouses produce quite similar wakes in that the flow from around the wheels and the wheelhouses stick fairly close to the ground as you travel downstream. So you can see here, these streamlines come around and they just stick like in the underbody sort of section downstream. On the other hand, when you put the Mercedes wheelhouses on the Ahmed body, the flow in the wake pops up and even to about halfway up the vehicle, so you can see the flow coming around underneath, and it just jumps straight up to like about the where the back of the trunk would be, or the back of the boot before the like windshield. So that indicates just from this that the wheelhouses from the Mercedes car would produce more downforce than the other two. But again, this is instantaneous, not average, so we need to take that tentatively, that conclusion. In figure 13, we again have instantaneous streamlines, but this time they are around the front of the wheelhouses, and if these instantaneous streamlines are indicative of the time averaged ones, then the flow is very different between all of these wheelhouses. So for example, the flow coming out of the Audi wheelhouse is far more chaotic than the other two, and it also seems to be much slower. You can see here, all this flow comes out of the front rim in particular, and it's very blue, and there's just so much of it, whereas for the RAV4 and the Mercedes, okay, there is some flow coming out of the front rim, but it's not nearly as much as the Audi, and it is faster moving flow. So from this isolated view, we might want to conclude that the Audi wheelhouses produce more drag than the other two, but there are two main factors we need to consider before truly concluding that fact. The first is that, again, this is an instantaneous view, so this might not be indicative of the overall flow physics. The second factor is that even if the view is correct, and the Audi constantly produces a greater wake, this is only a localized effect from the wheelhouse. This change in flow physics might positively affect the car in other ways that we can't see, and that is one of the major difficulties in car aerodynamics. There are so many components that affect each other that taking just one in isolation doesn't necessarily give us the full picture, and rarely can we make such a sweeping conclusion like, okay, the total drag of the car reduces. So yes, from this view it seems like the Audi wheelhouse produces more drag, but it may not be necessarily the case. If we were to look at, for example, the underbody or the rear wheels or the base of the car. So let's move on to the pressure distributions on the wheels. So in figures 14 and 15, we see the pressure distributions on the front and rear wheels respectively with the different wheelhouses. A is the Audi wheelhouse, B is the Toyota wheelhouse, and C is the Mercedes wheelhouse. So these are fantastic views because we can see so much. So the pressure distributions give us very good indications as to how much drag and lift are being produced by the wheels. All we need to do is look at the pressures on the front and back of the wheels, and at the top to get a decent idea of the drag and lift productions respectively. So if we look at the front of the wheel, for example, and we get really high pressure, then that indicates there's probably going to be more drag than if there was low pressure. And if we get very low pressure on top of the wheel, then that indicates that we'll get more lift. So from figure 14, which shows the front wheels, we can see that the Audi wheelhouse results in much more pressure on the top of the wheelhouse, on the wheel, sorry, than the other two wheelhouses. So you can see here, it goes up to about 5-10 pascals perhaps, whereas for the other wheels, they only really hover around -30 and even up to maybe -20 for the Mercedes wheelhouse, but it's not nearly as much as the Audi wheelhouse. So this tells us that the Audi wheelhouse makes the front wheels produce more lift than the other two wheelhouse geometries, for the front wheels I should mention. This may not necessarily mean that the entire car produces more lift, but this isolated view of just the wheel shows that the Audi wheelhouse produces more lift on the front wheel. I would also be inclined to say that the RAV4, the Toyota car, this wheelhouse makes the wheels produce less drag because there seems to be slightly higher pressure on the rear of the wheels than for the other wheelhouse geometry. So you can see here, this lighter blue color, which indicates like -40 pascals perhaps, comes down further than for the Audi wheel, and it's non-existent for the Mercedes wheel. So there's higher pressure on the rear of the RAV4 front wheel than for the other two wheels, and all else being equal means that there's less drag on this wheel. So let's look at the rear wheels now. So figure 15 shows quite a lot of variation between the wheels. For the rear wheels, there is likely more drag produced on the wheel in the Audi wheel housing because there is quite a lot more pressure on the upstream face. So we can see just here, there's like this red here, and I think that, I'm not sure how much it extends around, but the fact that we do get some red here indicates that there's higher pressure on the front of the wheel than the other two wheels. There's a little bit of red pressure here for the Mercedes, but I think it's more, from what I can tell at least, it extends more for the Audi wheel. So we can see kind of that the Audi wheel probably produces more drag for the wheel than the other two wheelhouses. Another interesting feature can be seen on the Toyota wheelhouse wheel, where just around the bottom front edge, so just here, there's this low pressure region. I'm not entirely sure what this is from. I think might be due to the jetting vortex, but without more information, it's hard to say that with certainty. So usually there's this jetting vortex coming around, and jetting vortices by nature are very low pressure, and depending on where it comes around, this might be due to that. The Toyota wheel, which is this middle one here, also experiences a lower pressure on the outside face, which might again be due to the stronger jetting vortex, or simply from more flow coming out of the wheelhouse further upstream and then going around the outside of the wheel. Now remember, from the other, what we saw here, this is for the front wheels, these streamlines. We saw for the front wheels, the Audi wheel had a lot more flow coming out of the front wheel, but for the rear wheels, we're not really too sure. So it might be the case that there is more flow coming out of this rear wheelhouse and causing this low pressure on the outside surface, or it might be due to the jetting vortex. I'm not too sure here. We don't get enough information here. So let's look at figure 16, which shows some vertical cut planes along the car's underbody. The first cut plane is only 5 millimeters from the ground, so this first one here, and case 1 is for Audi, case 2 is for Toyota, case 3 is for Mercedes. Then the second cut plane, which is this second row here, that is 22 millimeters from the ground, and the third cut plane, which is this one here, so that's 39 millimeters from the ground. So all are well below the car's underbody surface, so it's like the flow going right underneath the car underbody. So the underbody flow is quite different between all the different wheelhouses, which I'm a little bit surprised at. For example, the Audi and Toyota in the second and third cut planes, so these two here, like this, these four here, there seems to be faster moving flow hitting the rear wheels than for the Mercedes. So let's look here. Let me zoom in a little bit. Maybe we can see a little bit better. I guess this is okay. So if we look at the Mercedes one here, we can see that the flow coming around and hitting the rear wheels is quite slow moving flow. It's about 4-6 meters per second. For the Audi, which is these two here, and the Toyota here, you can see that there's more green, which corresponds to about 10, even 12 meters per second, which is hitting the rear wheels. So there's faster moving flow hitting the rear wheels here than for the Mercedes wheelhouse. Also, the flow from the front wheels on the Mercedes seems to bow out before coming back in. So we can see like here it blows out a little bit, blows out, and then it like sweeps back in. This doesn't really happen for the Audi or the Toyota, where like the flow is really a lot straighter. So that potentially changes the flow physics and even the drag and lift. So figure 17, let's move on to that, shows a very important view, is that the cross-sectional planes more and more downstream. So we get case 1, which is for the Audi, case 2 for the Toyota, case 3 for the Mercedes, and as we have like just at the rear of the vehicle, I'm pretty sure, then further downstream and further downstream again. They show that the total pressure contours are quite different between all these different cars. So if you don't know what the total pressure is and how it is different to the static and dynamic pressures, watch a video called Aero Fundamentals number 6 on our YouTube channel, where we go through exactly these and how they are different. And again, I think we did a pretty good job in explaining the difference of them, because again, they really need to be understood well. They're a fundamental concept, and if you can understand these, then you're going to do a lot better aerodynamics. Anyway, these cut planes show their flow evolution around the wheels to be very different. For example, the Audi, which is the top part here, seems to have less of a wake forming around the wheels compared to the Mercedes and even the Toyota. So we see here, like in this plane here, we get similarly bigger wakes, I think, around the Mercedes than the Audi wheels. For this plane here, they're a bit more comparable, but even this one here, you can see that the Mercedes has a bit bigger wake, and this is quintessential like wheel wakes. We get a bottom part, which is from the jetting vortex on each side, underneath and on the outside. Then on the top, there's another vortex coming around as well. So the wakes also pop up a little bit more for the Toyota and the Mercedes. So you can see here in this third plane, the wakes stay quite close to the ground for the Audis around the wheels. But then for the Toyota and the Mercedes, they pop up quite a bit more. And that is quite normal for regular cars. Like the Audi having such a smooth and like sleek wake is quite unusual for regular cars. So the final thing we're going to discuss in this podcast is the Q criterion for the front wheels, as shown in figure 20. There's a few other figures, but they don't really show too much. We're just going to stick to figure 20, which shows the isosurface of instantaneous Q criterion colored by values of velocity in the left front wheels for the Audi, Toyota, and Mercedes. So the Q criterion effectively tells us where vortices are. And you might be wondering why we don't just use vorticity. I mean, if there is vorticity present, shouldn't there be a vortex? Well, not necessarily. In fact, you can have a vorticity without a vortex present. So using something like the criterion or the lambda 2 method helps us be sure that a vortex really is present. If there is a value here of the criterion or lambda 2, then we can be sure that, okay, there's a vortex there. So one thing that is very obvious from these figures here is that there is a much bigger vortex over the top of the Audi wheel than for the other two wheels. Let me zoom in a little bit here. So, in fact, for some reason, for the Audi wheel, there is one big vortex right here. Like you can see this massive plane here. While for the Toyota wheel, there's just a lot of small junk. There's almost nothing here. And then for the Mercedes wheel, okay, there's a little bit of a vortex, like there are a few little cuts here, but not nearly as big as this Toyota vortex system here. Apart from that, they all look to produce many smaller vortices throughout the wheelhouse and rim region. So you can see here, there's just like a lot of little bits of junk coming off here, and they are of slightly different velocities, so they're moving at different speeds. But again, there's nothing really coherent that you can point out saying, okay, this is a major feature and it's different between these wheelhouses. The only real difference is that major sweeping one over the back of the Toyota wheel. So, and with that, my little aerodynamics, we come to the end of this podcast. And if you liked it, make sure to hit the like button. And if you want to see more like this, hit the subscribe button. And if you want to make your aerodynamic experiments 2 to 4% more accurate, get yourself an atmosphere hawk. It's an instrument that we make to accurately measure the density of air. And the reason why it's important is because the density of air constantly changes on a regular day. It changes between 2 to 4%. In fact, if you go into your wind tunnel in the morning and do some experiments, then come back after lunch, the density of air would have changed by that much, 2 to 4%. And it changes even more from day to day, week to week, month to month, and season to season. These changes are usually between 5% and 15%. And if you have an error of 15% in your experiments, then chances are that you can't find too much, and what you are finding is more to do with chance than reality. The atmosphere hawk gets rid of those errors for you, so you have accurate data. It also makes it much easier to validate your CFD because the validation data that you use is now accurate, and you can specify the exact same density in your CFD as you had in the wind tunnel. So for example, if you went to your wind tunnel and you specified a certain dynamic pressure and you think, okay, that's going to be the velocity of the wind tunnel, well, it's not actually that because you have 15% error in your velocity. And if you try to then go to your CFD and you say, okay, that's going to be the velocity in the CFD, well, that doesn't actually match your experiments because your experiments had a different density. So the atmosphere hawk is rid of that error for you. So you should get one and make your experiments better. You can find it in the link in the description. And if you want to get better at CFD and/or theory, check out our courses in the link in the description. And I'll see you next podcast. Peace, amigos.